The purpose of this lab was to examine the motion of a spring and determine if it obeyed the energy principle. Some fundamental principles that I used were the energy principle and Newton's second law. Using the initial data, analysis of a video and tracker, and a model in Python, I found that the motion of the spring does follow the energy principle. To initialize the data, I set the system equal to the spring and the earth. This means that no energy entered or left the system. Some given quantities were that the mass is equal to 0.402 kilograms. The starting point was given from the data from tracker. The initial velocity is equal to 0. The time step is equal to 1 over 210 seconds. And the initial length is found by rearranging the equation for the period and finding that the period times gravity divided by 4 pi squared is equal to 0.123 meters. So now I'll go ahead and run the video from tracker. As you can see, the spring oscillates and moves around. From the video, I plotted points of the motion as the spring swung around and outputted this data to a CSV file, which I later inputted into my Python code to compare to the model. Next, I used the energy principle to find the different components of the change in energy, which came out to be the change in kinetic energy, the change in gravitational potential energy, and the change in spring potential energy, which all equal 0. So as you can see, I found the kinetic energy by multiplying 1/2 times the mass of the ball times the magnitude of the speed squared. And you can read, so here are the other equations. And this I used to make a graph which showed the conservation of energy, which I'll get to later. But I also used Newton's second law to update the position of the ball, or the spring, that was oscillating around. Another note on the energy: the change in energy was found by subtracting the kinetic energy found from one iteration, and subtracting that from the previous kinetic energy. So now I'll run the Python code. As you can see, the gravitational force is always pointed down, and the spring force is pointed along the spring. The red ball shows the observed motion of the data from the tracker video. It's very close to the computer model, but due to the small number of frames per second of the video, it's not quite smooth. And so here we have the graph of each of the energies and the total energy in yellow here. As you can see, the total energy is 0 or very close to 0. You can see here that the spring potential energy and the gravitational potential energy are out of phase, which means that they'll cancel each other out. And the kinetic energy completes one period per each peak of the spring potential energy and gravitational potential energy. This means that the kinetic energy does not change. So now I'll run through the model again, this time graphing the observed position from the tracker data compared to the model prediction. And the simulation shows that the predictions are very close to each other. The observed data in red is slightly below the there's a slight gap between it and the model prediction. This could be caused by a little bit of drag force that wouldn't be accounted for, but it's very small compared to the motion. To answer the what does it mean question, my model did satisfy the energy principle. The spring potential energy and the gravitational potential energy were almost perfectly out of phase, and the kinetic energy completes about 1 period per peak of these. This means that there's no change in kinetic energy for the system, and the other energies cancel each other out. The periods for the data are slightly off, which could be the result of errors in measuring the data from tracker. So in conclusion, the data and the model both obey the energy principle and show that if no energy is added to the system, the change in energy is 0.